Hello, everyone. I'm excited to present to you today some work that I've been doing, and the title of this talk is Estimating Predation Thresholds for Persistence of Reintroduced Native Avifauna Following Suppression of Invasive Brown Tree Snakes on Guam. I've been collaborating with Evan Paxson at USGS, Andre Nguyen at the University of Hawaii, and Shane Sires at the USDA. So given a general interest in restoring Guam's native vertebrates and that efforts to suppress and monitor BTS are gaining ground, there's a growing interest in the opportunity to reintroduce birds to Guam. The problem is that we know very little about several key details. What I hope to do today is show you how my collaborators and I are quantifying the threat that BTS poses to Guam birds. Toward this objective, I identify the obstacles we faced, which primarily is a lack of information. I discuss the tactics that we've used to overcome these obstacles and predict bird population outcomes in response to reduced brown tree snake predation. The simulations we generate help to shape our expectations by identifying benchmarks and bracketing our uncertainty. We selected these 7 birds for our study. Some of them no longer exist in the wild, while the others persist on neighboring islands. Sully here is the only bird of these 7 that persists on Guam today. Similarly, for the brown tree snake, it'd be helpful to have each of these metrics pinned down, but this information is unfortunately out of reach currently. In particular, the lack of information concerning snake abundance and the versatility of their diets together make it difficult to predict attack rates. So to overcome the obstacle of sparse data in bird demographics, I'd like to acknowledge my collaborator, Andre Nguyen, who scoured the literature and reached out to scientists currently working with these birds to compile all the information available on these birds. With the information we gathered, we were able to define a life cycle progression for each bird species. I'm showing that briefly here. We used a variety of information to structure our models. For example, I show 2 slides here that I borrowed from Martin Kastner and Henry Pollack's presentations last November at the BTS Technical Working Group meeting. And this just shows the kinds of life history information and demographic metrics that we use for our 7 birds, in addition to fecundity rates and survival estimates that we may have been able to achieve or attain. We defined at least 3 basic life cycles for our 7 birds. In the first life cycle here, we defined pair bonding status as a requirement for breeding, and we allow if you're pair bonded or not pair bonded. If you're pair bonded, you can be either non-breeding, breeding, or parental care. In the second life cycle that we have here, we did this subadult stage to prolong the age of reproduction. And then in this one, we also cut out the pair bonding status. So all birds were considered to, or at least, have a chance of being a pair. And then in this third life cycle, we shortened the juvenile period a little bit, and then further shortened the breeding cycle. So I won't talk too much about that for now. We used these models to simulate individual birds within a theoretical founding population. And we obtained several demographic metrics of interest, but rather than go into each of these for now, I simply wanted to hint at the level of detail that we have in these demographic models. Because for now, what's truly new about what we're doing and more to our objective is determining how best to incorporate brown tree snake predation into predictive models. And this requires several steps and bits of evidence. So I developed this Bayesian belief network to help structure the conditional probabilities on encounters and of death on encounter given each bird's specific traits. Please note, we do not imply that any of these birds suddenly are not vulnerable to BTS. Rather, we assume that they're all highly vulnerable, but some may be less or more or less vulnerable than others. So it's important to still rank that. The rate of predation by BTS is a black box, so to speak. Theoretically, we can separate predation into the risk of being encountered and then the risk of death given an encounter. So for now, I'm gonna focus on the risk of brown tree snake encounters, and the evidence that we have here, the most reliable bit of evidence, is in the form of contact rates at live lure camera traps. So let's think about that for just a second. The rate at which BTS encounter live birds in a cage, so they have a caged bird and a camera on it, that may be the most reliable or the most relevant metric we have for BTS foraging behavior. It also appears to be the best way of monitoring BTS, and in using this, we conveniently avoid several issues that we encountered when we were trying to think about predicting predation rates from snake abundance. So in short, what we do is we interpret contact rates as the rate that brown tree snakes will encounter live birds living free in an area. From the bird's perspective, any single encounter could be fatal and final. A low daily rate could mean a high chance of encounter over a time period relevant to a bird's life. And for this reason, I scale up from a daily to a 2-month encounter rate, and I use 2 months because this matched the time step in our demographic models. It's a fairly fine scale among demographic models. Returning to our Bayesian belief network, we can now pursue the second component of BTS predation, the risk of death during an encounter. And this is something that we can't get from monitoring BTS. We just kind of have to know how birds and snakes would interact, which we can no longer observe in the field. Here we have anecdotes and limited observations, but not data. So to overcome this hurdle, we gathered the observations and professional opinions of researchers who have worked closely with one or more of our focal species. Specifically, we asked those closest to these birds to consider the outcome of an interaction with a brown tree snake, and we then collected their responses and condensed them into quantitative estimates that we can use in our simulations. So let's quickly step through our survey results. We found considerable belief in a difference among these 7 birds and how frequently each would be encountered by a brown tree snake, given a theoretical baseline tree snake abundance in an area. We also documented consistent belief in the shared risk among family members. So what this means is that a family member may be in close proximity to, all family members will be in close proximity to one another, and therefore at risk of being noticed by a brown tree snake that may have encountered, one member or the other. In other words, a single brown tree snake encounter may put multiple related birds at risk. We thought this was important to include. We also found that early life stages were ranked more vulnerable than adult life stages. So we have these early stages with high vulnerability and the adults being more low vulnerability. We asked that respondents drill down and try and pinpoint an adult survival rate or risk of death on encounter. And so they gave us these rankings here, which loosely follow a size gradient, but there's some differences in that. And then for a bird whose breeding partner is encountered, the risk of a shared encounter appeared quite likely, or at least non-negligible. So you can say that's equal risk there, or half the risk that the initially encountered partner would face. And importantly, we put all of these together for a quantitative estimate of the death risk on encounter for each life stage and for each of the 7 species. The benefit of this distillation of collective beliefs is that we can use these quantities as the best guess in our simulation models. So these predator encounter and death on encounter probability estimates feed directly into our simulations of theoretical bird releases on Guam into areas where we simulated fixed encounter rates. So altogether, this is how we defined the threat of predation by brown tree snakes for our focal birds. And from here, we can link these probabilities to each bird's population dynamics. Quite simply, the probability of being encountered multiplied by the probability of death given an encounter gives us the predation rate. And we link this into the survival rate for each bird that is species specific. We simulated hundreds of theoretical founding populations for each species up to a 20-year time horizon, and this is what we base our results on. So for the following figures, I have the annual growth rate on the y-axis and BTS encounter rate on the x-axis. The dotted line marks the replacement growth rate. Above the dotted line is the population is growing, and below the dotted line, the population is declining. We also varied the probability of death on encounter for each species to demonstrate our uncertainty in this risk. And these are shown in grayscale lines. And then finally, we simulated our survey estimates as our best guess at predation risks for each bird species, and these will be shown in color. So here are our results. The tolerable predation rates are where solid lines are above the dotted line. This is on the left side of these figures. The region of intersection between solid and dotted lines identifies our range of uncertainty in threshold predation rates. And the uncertainty that is due to our uncertainty in the risk of death on encounter. Where the colored lines cross the replacement boundary marks our best predation threshold estimate for each bird species. And in other words, it encapsulates our collective beliefs in the species-specific risks of death on encounter. So I'll show you these rates again here, because translating these bi-monthly encounter rates is crucial for their utility. And so if we want to translate them to nightly contact rates, which is where the monitoring is going, I plotted out this relationship between the two. And the ones I have highlighted here are what was shown on the previous slide. And these are then reflected across to the nightly contact rates, which we can then compare to recent contact rate observations in the literature. So we have the Amy Yackel-Adams estimate and others reported in this paper that was 0.18, contact rate of 0.18 per night. And then this other one that we showed for Pollock et al. Was one we calculated from their predation rates reported on fledglings in an area. The key takeaway from this figure is that the encounter rate thresholds that we estimate are 2 to 3 orders of magnitude lower than recently reported observations. So that's a pretty large number. And then it would be very useful to further translate these thresholds to a BTS abundance metric, such as the snake density per hectare. However, we currently lack the tools to do this. So I'll just move on and talk about the nightly contact rates. We present the following thresholds below which a reintroduction for each bird might reasonably begin to expect to find success. There are other threats out there, but in terms of just contact rates, they would need to be below this for these birds to persist. The final bit of uncertainty that we explored relates to the underlying demographics, which we defined for each bird. On a fundamental level, if you can think about the balance between the population growth rate and the predation rate as the point where the population is just replacing itself. Higher growth rates can support higher predation rates, for example. I used this equality to draw a surface of zero growth isoclines. It's what we have mapped here. And they map the relationship between the encounter rate, the contact rate here, the variance in the probability of death on encounter, and then the intrinsic ability of the population growth rate, the intrinsic population growth rate before brown tree snake predation. And I then plotted our estimates for each bird on this mapping, and I did this to illustrate how uncertainty in the rate of population growth rate might affect our results. If, for example, we grossly overestimated the growth rate of Sully, we can simply trace along the contour lines to our newly observed growth rate and then modify our expectations accordingly. I traced all of these to one common growth rate, and you can see in doing that, if they all had the same population rate of growth, then this reshuffles the expected BTS tolerances. Yes. So to wrap up, in summary, we built individual-based models that simulate founding populations of each bird species with the threat of predation by brown tree snakes. We codified our existing beliefs concerning the range of susceptibility to BTS among native Guam avifauna. We identified threshold contact rates that could signal a minimum requirement for safety of birds in a given area. And ultimately, we predict that something near eradication, at least locally, may be required for successful reintroductions of avifauna on Guam. There are many people to thank, in particular, all of the scientists listed here who participated in our survey. The collaborators are not listed here, but I'd like to thank them. Our funding sources, and Mark Hall for guidance and management, the Research Corporation of the University of Guam, and Sarah, Hannah, and Amy for useful discussions on this project early on. And I thank you for your attention. I'll stop sharing. Thank you.